Inside a vast hall filled with filtered air, figures in sealed suits move slowly between towering machines. Beneath bright white lights, polished silicon wafers rest inside delicate metal frames. Each wafer appears simple at first glance. A smooth circle reflects the light above it, yet hidden on its surface are patterns smaller than dust. These faint patterns will become circuits, tiny pathways that guide electricity through machines. From them, the modern digital world begins. Beyond the walls of these laboratories, billions of devices quietly depend on such circuits. Phones, satellites, vehicles, and data centers all rely on silicon processors. Invisible streams of information travel across the planet every second. Messages cross oceans in moments. Financial markets rise and fall in fractions of time. Behind every signal lies a microscopic calculation, and behind every calculation stands a chip built from etched silicon. For decades, only a small circle of nations controlled the most advanced chips. Their factories produced the machines that powered the global economy. These facilities were among the most complex structures ever built. Inside them, lasers and mirrors guided beams of light across fragile wafers. Each flash of light carved lines thinner than a human hair. Layer after layer formed until a functioning processor emerged. The process demanded extreme precision. A single flaw could destroy thousands of chips in an instant. Governments understood the importance of these tiny structures. Control over semiconductors meant influence over technology, security, and economic power. The ability to manufacture advanced chips became a symbol of national strength. Countries invested billions to protect their technological advantage. Export laws soon appeared like invisible walls. Certain machines and design tools were restricted to a select group of nations. These restrictions were meant to slow potential rivals. Without the tools of chip making, progress would stall. But in distant laboratories, engineers studied the problem carefully. If the main road was blocked, another path had to exist. Somewhere within the science of light and precision, a hidden opportunity waited. And quietly, the search for that opportunity had already begun. If you value stories that go beyond headlines and reveal the forces shaping nations, you are in the right place. At Polity Pictures, we explore the power, strategy, and history that define our world. Subscribe and stay with us as we uncover the stories that governments rarely explain and textbooks rarely simplify, because understanding power is the first step to understanding the future. In research centers across China, a new question began to echo through quiet laboratories. If advanced chip tools were blocked, how could progress continue? Engineers gathered around whiteboards filled with equations and optical diagrams. The traditional path to semiconductor power now stood heavily guarded. Most experts believed the barriers were impossible to cross. The machines required for advanced lithography were built by only a few companies on Earth. These machines guided powerful beams of light through complex mirrors and lenses. Their precision allowed circuits to be etched onto silicon at an unimaginable scale. Without them, the creation of advanced processors seemed out of reach. Yet some researchers began to look beyond traditional semiconductor science. They searched in fields that seemed far removed from computer engineering. In quiet university libraries and forgotten technical journals, a strange pattern began to appear. Techniques used in art restoration and precision imaging shared unexpected similarities with chip fabrication. Across Europe, specialists had spent decades developing tools to restore ancient paintings and fragile manuscripts. Their work demanded extraordinary control of light and color. Lasers were used to clean centuries of dust from priceless artwork. Optical scanners captured tiny cracks and textures invisible to the human eye. These instruments were designed for beauty rather than electronics. Yet their precision approached the delicate accuracy required in semiconductor manufacturing. Chinese engineers began studying these optical technologies with growing interest. If light could reveal the smallest details of a painting, perhaps it could also shape the smallest structures on silicon. This idea slowly evolved into something more ambitious. The act of etching circuits could be seen not only as engineering, but as a form of technical artistry. Patterns of light could become the brush. Silicon could become the canvas. Within research institutes in Shanghai and Shenzhen, small experimental teams started testing these ideas. They explored how artistic imaging systems could be recalibrated for nanometer precision. What began as curiosity slowly transformed into a new strategy. Instead of chasing the same tools used by Western chipmakers, China would search for a different method entirely. And in that quiet shift of perspective, the outline of a technological loophole began to emerge. While engineers explored new theories in their laboratories, another effort unfolded quietly across distant continents. It moved not through research papers, but through contracts, meetings, and unexpected business deals. Across Europe, many small technology firms lived far from the spotlight of global industry. Some specialized in laser calibration for museum restoration. Others designed imaging systems for high-definition printing. Their tools were built to reveal the smallest details of art and photography. Precision mattered deeply in their work, but few imagined their inventions could shape the future of computing. Many of these companies were small and highly specialized. Some employed only a few dozen engineers working inside modest laboratories. In boardrooms and quiet offices, representatives from Chinese technology groups began to appear. They spoke calmly about partnerships, investments, and new opportunities. For struggling firms facing rising competition, these offers often arrived at the perfect moment. Ownership changed hands quietly. In some cases, entire research teams relocated eastward. In others, the technology itself traveled across continents. Crates filled with delicate instruments arrived in Chinese research facilities. Inside were advanced laser systems, optical scanners, and rare calibration tools. At first glance, these machines looked designed for artists and museums. Their purpose had been to reveal beauty hidden beneath centuries of dust and paint. But inside new laboratories in Shanghai and Shenzhen, their role began to change. Engineers carefully dismantled and studied each device. Lenses were adjusted. Software was rewritten. Lasers were pushed beyond their original limits. Gradually, the machines began to operate with new levels of precision. Beams of light were directed onto silicon surfaces with astonishing control. The same accuracy once used to restore a brushstroke now shaped microscopic circuits. Inside sterile fabrication rooms, light carved delicate patterns across silicon wafers. Each adjustment brought the technology closer to the world of advanced semiconductor manufacturing. What began as a collection of artistic tools slowly transformed into a new form of industrial machinery. And quietly, far from public attention, the science of light was being reshaped for an entirely different battlefield. Inside advanced fabrication laboratories, engineers now worked with tools that once belonged to a very different world. The instruments had restored paintings and scanned ancient manuscripts. Now they faced polished silicon wafers waiting beneath bright laboratory lights. At first, the experiments moved slowly. Small beams of light traced delicate paths across silicon surfaces. Engineers measured every reflection and every microscopic distortion. The challenge was not only technical but also conceptual. Traditional chip manufacturing relied on rigid industrial systems. These new methods required a more fluid understanding of light and pattern. Researchers began studying the behavior of light as if it were a living material. Every lens, mirror, and laser adjustment changed the final pattern carved into silicon. The work sometimes resembled the restoration of a masterpiece. Just as conservators revealed hidden layers of paint, engineers uncovered new ways to form precise structures on silicon. Gradually, the process became more refined. Light was guided through custom optical paths designed to control every fraction of a nanometer. Each new experiment produced wafers covered in increasingly complex circuitry. Tiny pathways began to emerge with remarkable clarity. The laboratory atmosphere grew more intense. Teams worked late into the night studying microscopic images projected onto large digital displays. Artificial intelligence soon joined the effort. Powerful algorithms analyzed millions of possible circuit patterns, searching for designs that traditional methods had never considered. The results surprised even experienced engineers. Circuits generated by these systems often appeared unconventional, almost artistic in their arrangement. Yet these unusual designs proved highly efficient. Electricity flowed through them with less resistance and greater speed. Fabrication plants began adapting their production lines to support the new patterning techniques. Machines that once followed strict industrial templates now operated with greater flexibility. Slowly, the boundary between engineering and artistry began to fade. Silicon wafers became canvases for patterns shaped by both mathematics and imagination. What had begun as an experimental idea was evolving into a new philosophy of manufacturing. And deep within the glowing laboratories, a different approach to semiconductor creation was taking form. Years of quiet experimentation slowly built toward a single turning point. Inside large fabrication plants, engineers prepared to test a new generation of patterning techniques. The rooms were filled with towering machines and endless rows of silicon wafers. Every surface reflected the soft glow of sterile laboratory lights. Engineers watched carefully as the first wafers entered the new optical systems. Lasers moved across their surfaces with controlled precision. The process unfolded layer by layer. Thin patterns of circuitry formed gradually across the polished silicon. Each completed wafer was examined under powerful microscopes. Images revealed structures so small they could barely be measured. At first, the results were uncertain. Some wafers carried tiny distortions. Others revealed circuits that worked but lacked full efficiency. Teams adjusted lenses and recalibrated their machines. The experiments continued day and night. With each improvement, the patterns became sharper. Lines grew thinner and more precise than earlier attempts. Eventually, the measurements revealed something remarkable. The structures now approached the scale of the most advanced chips produced anywhere in the world. Engineers studied the data in quiet disbelief. Years of searching had led to a working solution. The breakthrough meant that advanced processors could now be manufactured using techniques developed largely inside China. Factories began preparing for larger production runs. Conveyor systems carried growing stacks of wafers toward assembly lines. Artificial intelligence helped refine the chip layouts even further. Algorithms explored new arrangements that balanced power consumption with performance. These processors were not simple copies of earlier designs. Their architecture reflected the unusual methods used to create them. Circuits curved and branched in patterns rarely seen before. Yet they delivered impressive efficiency once electricity began to flow. By the middle of the decade, the new chips started appearing inside data centers and specialized electronics. A quiet milestone had been reached. The long search for an alternative path in semiconductor manufacturing had finally produced a working result. Across the global technology industry, the first signs of change appeared quietly. Engineers studying new processors noticed unfamiliar design patterns etched across the silicon. These chips consumed less energy than many expected. Their unusual circuitry allowed data to move with surprising efficiency. Technology analysts began examining the manufacturing methods behind them. Reports slowly pointed toward a different style of fabrication emerging in China. At first, the reaction was cautious. Western semiconductor companies had dominated advanced manufacturing for decades. Their factories relied on complex systems refined over many years. Entire supply chains had been built around these traditional methods. But the new processors showed that another approach was possible. Optical patterning and flexible design strategies were beginning to compete with established techniques. Inside major technology conferences, conversations grew more serious. Engineers discussed how these developments might reshape the future of chip manufacturing. Some researchers became curious about the new laboratories appearing across Chinese technology hubs. Facilities in cities like Shanghai and Shenzhen were expanding rapidly. These centers offered vast resources for experimentation with optics and photonics. Scientists were encouraged to explore ideas that once seemed unconventional. Gradually, specialists from around the world began accepting research positions there. Optical physicists and imaging experts found new opportunities to push their work further. This quiet migration of talent strengthened the growing ecosystem. Meanwhile, global markets began to feel subtle pressure. Companies searching for specialized processors increasingly turned toward new suppliers. Data centers and artificial intelligence systems demanded chips that balanced speed with energy efficiency. The new designs provided an appealing option. Western manufacturers watched the shift carefully. Some attempted to adapt their own research programs towards similar optical techniques. But change in large industries moves slowly. The infrastructure built over decades cannot transform overnight. Across the semiconductor landscape, the balance of influence began to tilt. What had started as an alternative experiment was now reshaping the direction of an entire industry. As the decade moved forward, a new vision of computing slowly began to take shape. Engineers no longer viewed light only as a tool for carving circuits into silicon. Instead, light itself started to become part of the computation. Inside research facilities, delicate experiments explored how photons could travel directly through microscopic channels on a chip. These beams of light carried information with incredible speed. Unlike electricity, light moved without resistance through carefully designed pathways. Signals could travel faster while producing far less heat. The idea transformed how scientists imagined the future of processors. Silicon wafers were no longer just platforms for electrical circuits. They were becoming landscapes where both light and electricity worked together. Tiny optical pathways began appearing alongside traditional transistor networks. Within these structures, pulses of light moved through channels thinner than a strand of hair. Artificial intelligence systems soon benefited from this approach. The enormous calculations required for machine learning could be handled more efficiently when light carried portions of the workload. Manufacturers started exploring how these technologies could be integrated into consumer electronics. Data centers, advanced phones, and specialized processors all stood to gain from faster communication inside their chips. the change carried deeper implications as well. Nations that once dominated semiconductor manufacturing now faced a different technological landscape. The center of experimentation had begun shifting toward laboratories willing to explore unconventional methods. The race for computing power was no longer limited to building smaller transistors. It now involved mastering the delicate movement of light across microscopic surfaces. Decades earlier, the semiconductor revolution had been driven by electricity alone. Now, a new era was beginning to emerge. In laboratories glowing with quiet white light, engineers continued shaping patterns onto silicon wafers, but within those patterns, something more powerful was beginning to flow. Light itself had become the next language of technology. The world is changing faster than ever, and every nation carries a story that shapes the global balance. At Polity Pictures, we bring those stories to life through cinematic journeys into power, politics, and history. If you seek depth instead of noise, perspective instead of propaganda, this channel is for you. Subscribe and join us as we continue exploring the forces that move the world. The next story begins now.